All right, so we're talking about hardware routing. So the idea is we have messages we want to send from one computer to another computer, or maybe from a fax machine to any kind of machine. So we'll call them nodes. And there's different ways of connecting them together to get data across. So obviously we could do things in software, right? You could look at the IP address and you could say if the IP address equals this number, send it here. If not, see if it matches another one, send it here, and you're running through software, and that could take a lot of time. So it'd be nice if we did this through hardware. So we talked earlier in the semester where we said each machine has its own IP address. And in IP version 4, there were 32 bits for the address of your machine. And IP version 6 is going to be 128 bits. But in this example, let's pretend the address of your machine was 3 bits. So here's machine 000, 001, and it goes down to 007. And we wanted to, so this is a computer here, 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 here. We have 8 computers. And we'd like to be able to connect them together so any computer can send a message to any other computer out of the 8. So if you're on computer 000 and you want to send a message to some other computer, so just randomly pick one. Which one would be good?
100.
100? So this one, number 6. So what we're really doing is you could kind of think of this shuffle exchange as a tube. Like this machine wraps around to here, so that there. So what we're doing is, so we want to connect from, we want to send a message from 000 to 1. Did you say 110?
100. This is target.
This one, 100?
Yeah.
Okay. So what we can do is we want to get the message as quickly as possible, and rather than say in software, if machine is you're sending it to is 001, send it. If it's 2, send it along a 2-pad, 3 along a 3-pad. What we'll do is we can compare the first bit of the source to the first bit of the destination. And if the bits match, if this 0 and this 1, if they don't match, then when we send the message into this box, if the first bits don't match, well, if they did match, we would send it across to here. And if it doesn't match, we crisscross and we send it to this one. So it's just you compare the 2 bits with an XOR and ask if they match or not. If they match, the data gets sent from this point to this point. If they don't match, it gets sent from this point to this point. So the 0 and the 1 don't match. So the data we're trying to send, a line is connected that goes to here and then down to here. Now we're in the second box.
Yes.
We compare the second bit, this 0, to this 0, and they match. So the data goes across from here to here. It doesn't crisscross, it goes straight across because the 2 bits match. So now it comes out of here and goes down to here. And then the third bits, 0, and 0, they both match, so it gets sent across here. So the path would go, the message would go like this. It would crisscross, come down, go straight across, come down, and go straight across. So it's just at each stage, each of the stages has inputs into them that compares 2 bits and very quickly, so that the time to run an XOR gate is very quick. And then we know whether we should have the lines connected or crisscrossed. So the message could get routed pretty quickly. Now obviously, this is a small example because we're just using 3 bits. If we had more bits, we'd have to have more stages. But we could connect very quickly. So what are some limitations on using the shuffle exchange? Well, for example, if a message has to go from node 0 to the one you pick, node 4, we would have to set each of these stages to let the message go from 0 to 4. So if any other nodes needed to communicate, they'd have to wait till the message went through. Then they could use the exchange. Okay. So there's different ways you can connect nodes together. The more connections you have, a lot of times, there's good and bad to all the methods. So the more connections you have, the easier it is to Right. Easier it is to directly connect to nodes together, but the more expensive it is. So for example, we could have point-to-point connection, connection directly between the nodes. A bus connection is where nodes are connected by a single cable. So that's kind of, well, actually I have some pictures after this, but that's kind of like everyone lives on a street, so all the houses are connected to a street, so you get from house to house. A star network is where each of the nodes are connected through a central one in the middle, doing all the work for you. A ring is where they're put into a loop, so if you want to send a message from one node to another, you send it around the loop till it gets the message it went through. And then kind of a hybrid of those is what we'll call a mesh network. So the pictures kind of look like this. We have a ring, so all the computers are connected together. Each one is connected to, has a left and a right. And if you want to get a message from, let's say, this computer to this computer, well, there's two ways we could do it, right? One is you'd have to send it to this node who says, oh, this isn't for me, and I'll pass it to this node, and this one will read the message, read the destination, and say it's not for me, and just pass it to the next guy. You don't have to do a lot of thinking, you just say, if it's not for you, send it to the next one. So it goes this way. You could also have sent the message this way. And if for some reason one of these communication links broke, we'd also have the second path. You could go to the left or to the right to get the message across. So the star is the case where I'm going to skip the mesh for a little while. The star is the case where every node, there's one node that's picked as to be like the center of the network. And every node is connected to that node. So if you want to send a message from this node to this node, you always send it to the center, and the center routes it to where it's going. So there'd always be two hops. So the more nodes you have, the more you're plugging together, the more work you're putting on the middle one. Another one where you might say, well, so far all of the network connections we've talked about, if one node is sending a message to another one, all the other ones have to wait because they're utilizing the same resources to get the message. They have to wait for the message to go through. And then they can go next. If everything was fully connected, then this node can send a message directly to this node, and it doesn't affect anybody else because you're using this line. And if this one simultaneously wanted to send a message to this one, it could use this one. They're independent of each other. So this is obviously a lot more expensive. And then when you go to send a message to another node, if this one wants to send a message to one of these addresses, it has to somehow check them all and find the one that matches the destination address. Now, if it's small enough, we could do this using hardware. We could use kind of like the translation look-aside buffer. We simultaneously check the address we're sending the message to against all of these addresses and find one that matches. And if it matches, the line gets turned on and the message gets sent along that line. So we could do that if it's a small enough, fully connected network. A line is a pretty similar, same idea. Is just you'd have to know wherever your location is your message going to the left or to the right, and you just keep passing it. The next node that gets it reads it. If it doesn't match their ID, they send it somewhere else. And so then, again, this is going to have a lot to do with how much time it takes, how the nodes are connected together. A tree structure is basically a network that has no cycles in it. So if you take an algorithms class, the definition of a tree is a collection of nodes where there's no cycles in it. So here we have a cycle, and in this case we'll get to a little bit later. We have a cycle here, we have a cycle here. This has two cycles. If a network has no cycles in it, it's referred to as a tree. And so trees have a lot less connections to them. One downside is if ever in a tree a connection goes down, you've broken the network into two pieces. So if this link right here ever went down, you couldn't communicate from here to here. Because it's a tree, there's no cycle, so there's no alternate path to get from one point to another. And then the bus setup is where there's a line, this is kind of like a street running down in a block in a neighborhood, and these are houses connected to the street. If you want to get from your house to some other house, you have to go out to the street, drive down to the house, and then go into their driveway. So that's kind of the idea of a bus. So a mesh network is kind of a hybrid of all of these. That they're not fully connected. There's no requirement that there be one in the middle that everyone connects to. There's no requirement that it's a tree, meaning no cycles. You can have cycles. And so it's just any combination of connections between nodes. So in a case like this, if you wanted to communicate from, let's say, this node to this node, what would we have to do? If you pass the message from this machine to this machine, and this one says, well, that's not my IP address, I'll pass it along. Who do they pass it along to? It has 3 places to go. And if, let's say, we make it a little difficult, I want to go from here to here. This one is not directly connected to here, so what would be the best way to go? Or how could you make a decision, which is the next stage? If you send a message from here to here, and your goal is to get to here, this one gets a message, reads the IP address of where it's going, says, this is not me. I have 3 places I could send it. How would it pick? What's the best way to send it?
Shortest path.
Yeah, okay. So yeah, did you take that in the algorithms class? Or?
I have studied in the bachelor's.
Which class?
Undergraduation.
Undergrad.
Oh, okay, all right, right. So now the idea is don't just send it anywhere, but now we'd have to, we want to calculate the shortest path to the destination. So when you get to here, the shortest path algorithm doesn't say how much time does it take to get to here, or here, or here, and just send it to the shortest one. It says, well, I have to add this link to this link, and I have to add this link to this link, and then pick what's the best one. So there's an algorithm that has to run, and the algorithm can't be run in hardware. So this requires that each node can run the shortest path algorithm. One way you can do it is you can have one node dedicated as like the central hub that calculates all the shortest paths. The other one is you could just send it to each one, and then each one at that stage says, for the remainder of the trip, what's the shortest path? But that means you're kicking off an algorithm every time the message arrives. And what our goal is to get messages around the network as quickly as possible. Okay, yeah, so just a couple of comments on each of these styles. So the token ring is a local area network where, so that's the ring where you want to pass a node to, you want to pass a message from one node to somewhere else on the ring. You pass it to the guy next to you, he looks at it and says, this is not my address, he'll pass it to the next guy. They just keep doing that till it hits its final destination. So the token is basically the IP address, or the address that says whether it belongs, the message belongs to you or not. So when the token ring was originally invented, they used 24 bits, not 3 bits, like in our example, as the IP address, and you just work your way around the ring until the message gets to where it's going. So now you get into the issue where if the message is going in one direction and message is in another, they're going to collide with each other. So you might have to have times where only one node can communicate to another. Once the message is completed, you can now start another communication. But it's very inexpensive and easy for error checking. Communicating by a star, so a star where there's one node in the middle, so we have a hub and some leaf nodes. So a star is a special type of a tree, right? There's no cycles in it. Data on the star network passes through the hub or the switch, whatever you want to call it, before getting to its final destination. So there's at most 2 hops, and that hop in the middle has to be the coordinator for all the other hops. Okay. Communication through Ethernet, so that's, most of the classrooms at this university have a yellow wire coming in, but now it's popular to use blue wires. But that's an Ethernet connection. So there's an Ethernet connection running through the building, and every classroom is connected to it, kind of like a bus. And the thing is, and this kind of shows up in security, when a message is being sent to any computer in this building, every computer gets a copy of it. and it looks at the IP address it's supposed to come to and says, oh, that's not me, so I'll ignore it. But you could you could play around with the program and say, I want to see the message anyway. So now messages being sent to other computers, we could get a copy of it. So, and the way, again, speed is the most important thing. The way Ethernet works is our processor has an interrupt register, right? When we talk about interrupts earlier in the semester, the popular hardware design for interrupts is to have a register with a number in it, and it's popular to use the number 0 means no problem. So you could have a register, if it's all zeros, you AND all the you OR all the bits together, and if ORing all the bits together is still a 0, that means there's no problem. So the processor can just keep running instructions without any error. If a message comes in along the Ethernet, it puts a number in the interrupt register saying message coming in from Ethernet, and that would interrupt the CPU and then start handling that message coming in. So Ethernet is it's bus style connection of computers together, and it runs on an interrupt basis. Okay. And then, yeah, like you said, the mesh, the most interesting thing about the mesh, since it is a hybrid of all the other connections, certain nodes can be connected to each other, links could go down, new links could get added, so the connections could keep changing, and it's not fully connected. So anytime you want to go to send a message from one node to another, it's going to be based on all the current connections, and the node probably should calculate the shortest path algorithm to know what's the best path to get the message along. And also the self-healing is, so the network is in such a way that links could go down or could have just too much traffic on it, so it's effectively considered tied up. And then it's basically that link is not in use anymore. So you'd want to route it through another node. Okay. And then, so you can have, for example, a network. So basically saying if your IP address is broken up into two parts, the network number and then the machine, the host on your network. And what we can end up doing is connecting the network to a switch that then routes to different machines or even clusters in our company. So we could have cluster A, which is, a cluster is a collection of computers networked together. And we can use an internal MAC address. That's a kind of like an IP address, but internal to our company, not external to the internet. And then based on whatever port numbers that are assigned to the traffic coming in, we can assign it to either a cluster or a different network on a system. Okay. Yeah, so this is kind of, this topic kind of overlaps computer architecture and can even get into network security, because as you're sending messages from one machine to another, the network plus machines connected to the network could either accidentally or maliciously get a copy of the messages you send. So, so it's a little bit of hardware routing, but also just getting into another topic of like cybersecurity on networks.